All right, so any major questions on the midterm? We'll go over it obviously on Tuesday after it's graded, but anything that'll keep you awake over the weekend? Sorry? What grade did you get? Yeah.
Let's say you kind of messed up on something very on a small detail. How much is that? How much are like the points scored?
Oh, it's hard to say. So usually when I grade these, so like, there's a question, write a truth table from this equation. Let's say you put an extra 1 in the truth table. Okay, so, I'll take off a point or 2 for that. The next thing says, make a K-map for that. Well, you're going to have an extra 1 in the K-map. I'm not going to take off points for that again. Right, so usually, as long as I can follow your work and I know what you're doing along the way, if you, glitch out and you put an extra 1, you change a 1 to a 0, something like that, it costs you a couple of points and it's not going to like snowball into the whole question, as long as I can tell what you're doing, right?
Right. Yeah, because this is because like that first question was like for taking binary addition, it's like if I get this wrong, I will get out.
Oh, yeah. So if you convert the number wrong, but then you add the wrong number correctly, you get credit for doing the addition.
I did check at the end, and it did work, and I did get the right answer.
Okay. Okay. Yeah. I usually try to like see what happened along the way and. Any questions on Lab 4, which is due Tuesday, so this is our last class to talk about it.
The chip that I guess takes the 3 bits.
Mm-hmm.
There's like two other inputs.
Yeah.
A few more. Like, how do we hook those up? Because I feel like we have to do that.
Well, yeah, you always want to hook up inputs one way or another. So let's look at this. This is the 74LS47. So we're trying to generate outputs that make the display look like, a 0 or a 2 or whatever. And there's a lot going on in this table, but most of what we're interested in, we can look at this left column which says decimal or function, and we can look at the outputs. So suppose you've got 3 sum bits, so if you're calling those S2, S1, S0, and let's say those are all 0, you would like your display to look like this, right? So it looks like the character 0. And if you look at this table, that first row says everything is on except for segment G. So let's draw this chart. And I think it goes like this. Right, so to display a 0, we want G to be off, we want everything else to be on. And lo and behold, that's what that first row corresponds to. Okay, so let's make a table here. We've got DC, BA, LT bar, and RBI bar. So and I'm just going to copy from the first row of that table. I want LT bar to be high, RBI bar to be high, and I want DC, B, and A to be 0. So I'm just making my own subtable over here. Okay, now if my sum happens to be 0, 0, 1, then I want my display to look like this. So I want B and C to be on, everything else off. And magically, that's what the second row of the table corresponds to. B and C are on, everything else is off. So the inputs for that, LT bar should be high, RBI bar says don't care, DC, B should be low, A should be high. So I'm going to stick to 1s and 0s. So this is a 1. This is a 1, this is a don't care, and then these should be 0, 0, 0, 1. And we're not going to do this for the whole table, but you can see that for all these other entries, LT bar should be high. RBI bar says, I don't care. And D for these first few rows always looks low, and CBA looks like they just count in binary, right? 0, 0, 0, 0, 0, 1, 0, 1, 0, and so on. In fact, it looks like, let's just go ahead and do one more row here. For 0, 1, 0, this is what DCBA look like. Yeah.
Okay, so basically D should always be maybe hooked to ground.
D should always be hooked to ground, okay? That's going to save you a lot of time, because if you forget that, you're going to get weird symbols on your display, right? So what's the largest value that we're going to see on S2, S1, S0? 6, good, because that's 3 plus 3. That's not 6, that's 6. Right, and so in all these cases, D gets connected to ground. LT bar I would connect to VCC through a resistor. RBI bar I would connect to 1 through a resistor, right, 5 volts. Because in these cases it doesn't matter, but in that first row it suggested that RBI bar should be high. So connect LT bar, RBI bar to 1, connect D to 0, and then S2 goes to C, S1 goes to B, S0 goes to A. Hook up power and ground, hook the 7 outputs to your 7 segment, and you should see glorious digits. And if you see these kinds of symbols popping up, you didn't connect D to ground correctly. So we're basically using this like something that converts a 3-bit number to one of these displays, right? Which means we're ignoring the second half of the possible inputs, which is where D is 1. All right, other questions? All right, so let's keep talking about memories. So we had this circuit we were starting to look at on Tuesday. We had 2 inverters. Output of 1 feeds the input of the second. Output of the second feeds the input of the first. And we couldn't know whether that was going to be outputting a 1 or a 0 from one of the inverters. But whatever value that second inverter was outputting, that was going to be the value it continued to output. And if we could somehow change it, if we could short it out momentarily, then it would continue to output whatever that new value was. And so we want to make a proper version of a 1-bit memory using that concept. But instead of inverters, we're going to use a NOR gate. So let's look at what NOR does. So NOR is just the opposite of an OR. So normally the OR of this would be 0, the NOR is 1. The OR of these 3 rows should be a 1, so the NOR is a 0. But we noticed the other day that we could also think of this as something like an inverter that we can turn on or off. If we take a 0 and we put it into B, then the output is just the opposite of A. But if we take a 1 and we put it into B, the output is always a 0. So it's like an inverter that we can either turn on or turn off. When we turn it on, it just inverts. It's like a triangle with a circle on the end. But when we turn it off by setting B to 1, now it just says 0, 0, 0. It's all it outputs, 0. So we're going to build the following circuit. Here's a NOR gate. Here's a NOR gate. And this is how we had our two inverters connected. I'm just drawing it a little differently.
Is this called a flip-flop?
This is going to be a flip-flop, yeah. Exactly.
Yeah, right about it.
Okay, cool. So we have one NOR gate, the output's feeding to the input of the second, the output of the second is feeding to an input of the first. NOR gates have an additional input. And I'm just going to label these as inputs. So I'm going to label this input R, and I'm going to label this input S. And I'm going to label this output Q, and I'm going to label this output Q bar. Now we don't normally label outputs with bars on top of them, or we wouldn't have an output called A and B. This is really just kind of a convention. The way this works, this is always going to be the opposite of that. So when you look up these things called flip-flops or gates, you'll see an output labeled Q bar, and it means that it's the opposite of Q. But for now, let me just call it Q2. And we'll see that it's always the opposite of Q. Okay, so the task at hand is to analyze this circuit and try to understand what it does. And it's a circuit that depends on what's happened in the past. So we can use timing diagrams to help understand this. So let me make a trace for R, and a trace for S, and one for Q, and one for Q2. And I'm going to let R and S begin as zeros, so they're going to be low. And sometimes when you see timing diagrams like this, you'll see a little dotted line in the beginning. Just to show you that if it was high, it would be up here. Since it's down here, we know it's low. Otherwise, you just see a line. Is it up or down? I don't know. So this is just sort of to orient. This is at the low level. This is at the low level. And let's just suppose that Q is initially low also. We don't know if it is or not, but let's suppose Q is low, and let's see what Q2 is. So this is a 0 up here at Q. That comes down and feeds into our NOR gate. So our first input to the NOR gate is a 0. S is also a 0, so we've got 0, 0 going into a NOR. So what is Q2? Q2 is 1, right? 0, 0. Q2 is going to be high. So initially, if Q is a 0, Q2 is 1. Now here's the tricky part. Q2 is actually one of the inputs to this first NOR gate. So we have a 1 going in on this input, and R is a 0, so we have a 0, 1. If you put a 0 and a 1 into a NOR, what's the output?
0.
Just a good old 0. So this thing is going to output a 0. Q is going to stay low. Okay, so you kind of chase these signals around, and right, if we do this with one inverter or 3 inverters, we see the output keeps flipping back and forth. If we do it with 2 inverters or with 2 NOR gates set up like this, the output is stable. So Q is 0, Q2 is going to be 0. That's going to persist unless something changes. Well, so here's a change. Suppose that S changes from a 0 to a 1. And so in these timing diagrams, you'll also see something like a dashed line where things happen so that you can help line up these events. All right, S has become a 1. S is just an input to this NOR gate, so the only thing that's going to be affected initially are the inputs to this NOR gate. We've got a 1 going in. The other input is coming from Q, which is a 0. So we have a 0, 1 into a NOR. The output should be 0. So a little while after S goes high, Q2 is going to go low. And I'm not too worried about propagation delays here, so I'm just drawing a little bit of a delay there just because it's not instantaneous. All right, Q2 goes low, so now we have a 0 going into this input on the NOR gate. R is still a 0, right? We haven't changed R. So now we got 0 and 0 going into this top NOR. the output should be a 1. So a little while after Q2 changes low, Q is going to become high. And now Q is high, we've got a 1 and a 1 going into the NOR gate. On bottom, 1 and 1 should NOR to a 0. That should make Q2 low. Q2 is already low. So this is perfectly stable now. All right, next event, we're going to drop S back to 0. So what happens? S is 0, Q is 1. So now we've got a 1, 0 into this bottom NOR gate. Output should be a 0. That's Q2. Q2 stays low. No change there. Since Q2 doesn't change and R hasn't changed, this is still a 0, 0 going into Q. 0, 0 should give you a 1. Q is going to stay high as long as we don't touch R. Yeah?
So is there like a set way that, like, so if, for example, like R is going to be a 1 and S is going to be a 0, is there any like set way that it's going to read which, like a certain input first, or is it so fast that they're going to just not really care?
So you're talking about race conditions, which ties into glitches. In this case, it's not going to make any difference, right? Because the only thing we're changing is S, right? So we raised S, and some period of time later, Q went high, and then Q2 went low, and then we drop S. Now, if you raise both S and R at the same time, and one of them gets to its NOR gate before the other, that can definitely change what the circuit does. And those are big problems, right? And so when we introduce a clock, which is where this is heading, we'll try to get rid of those race conditions. All right, so what happened here? We had a circuit. Let's see what the circuit looks like in a system diagram, and then we'll come back to analyze it more. We got two inputs, R and S. And I'm not going to worry about Q2 for now. Let's just think about R, S, and Q. So when we started, Q was low. We raised the S input, right? We took this from a 0 to a 1, and suddenly our output Q went high. And then when we brought S back to 0, so we were back to both of these being 0, Q stayed high. Right? So Q is remembering that we raised S to be a 1 for a little bit. Might have happened 5 years ago. But it still remembers that S was a 1, and when S became a 1, Q jumped up to a 1 to say, hey, someone raised S. So initially R and S were low. Now R and S are still low, but Q has changed value. Okay, that's a memory. It's recording the fact that in the past, S was a 1. Even though it's a 0 now, right here, Q is high, saying, hey, S used to be a 1. Okay, so now let's see what R does. So we're not going to touch S, we're going to leave S low. But at this point, we're going to raise R. Well, if R becomes a 1, Q2 is a 0. So let's just bring these out to here. Q2 is a 0. So we got a 0 coming into the bottom. R is a 1, so we got 1, 0 going into our NOR gate. Output in the NOR gate should be 0. That means Q is going to go low. So R goes high, a little while later Q goes low. If Q goes low, we've got a 0 going in this part of the NOR gate. S is low, so we've got a 0 here. 0, 0 into a NOR, output should be a 1. So a little while later, Q2 goes high. And now that 1 comes up around here on the diagonal, comes in here. We've got a 1 going into the bottom. R is a 1, so we got a 1 going in the top. 1 NORed with 1 should be a 0. Q is still going to be low. So as long as R stays high, everything is stable. And now let's drop R. So this is a 0, Q2 is a 1, so we got 0 and 1 in an OR, output is 0, Q is still a 0. So Q is going to stay low. And since Q hasn't changed and S hasn't changed, this is still a 0, 0 going into a NOR. The output is high, Q2 stays a 1. So our circuit is stable again. So we have a circuit that we can use to record either a 1 or a 0. If we want to record a 1, we just raise the S line and then drop the S line, and the output's now a 1. If we want to change the output to a 0, we raise the R line and then drop it, and now the output is a 0. Okay, but the trick is it's sequential. Right, so what is Q if R is 0 and S is 0? I don't know. We can't make a truth table for this. Because sometimes R and S are 0 and Q is low. Sometimes R and S are 0 and Q is high. And then a little while later, maybe R and S are 0 and Q is low. So it's not a truth table kind of thing. It's not a combinational circuit anymore. It's a sequential circuit. It depends on the values of these in the past as well as their current values. So that's a memory. And we can build every kind of memory that we're going to use in the rest of the course from this one circuit. Right? We just keep adding on this. And eventually we're going to talk about a type of memory called a flip-flop, but this is not actually a flip-flop yet. This is something we can call a gate. And we just kind of unimaginatively call this an SR gate. And we can think of S as being a set input, and we can think of R as being a reset input. And since Q is always the opposite, since Q2 is always the opposite of Q, right, that's why we call this output Q bar. Now the one thing we didn't look at in this timing diagram is what happens if S and R are both high. And that's kind of an abnormal state. Because the explanation when you buy this thing from your corner market is if you want to store a 1, raise the S line and then drop it. If you want to store a 0, raise the R line and then drop it. What if I raise both lines? Well, that's typically an undefined behavior. But let's see what happens. So let's raise S, and Q will go high, and Q2 will go low. And while S is high, let's go ahead and raise R. Alright, so R is a 1. That's going to force Q to be a 0. Right? Because any time that one of our inputs is 1, Q is going to be 0. So as soon as R is raised, Q is going to go low. And if Q is a 0, but S is still a 1, 0 and 1, that's going to become a 0. Q2 is going to stay low. So at this point, Q is a 0, Q2 is also a 0. So this label that we put where this is Q bar and this is Q, Q bar should always be the opposite of Q. Well, it doesn't happen if R and S are both 1. If R and S are both 1, these are both 0. But we usually say this is a forbidden state. And we just say, don't make both R and S 1 at the same time. It's like hitting the gas and the brake at the same time in your car. You can do it and something will happen, but you're kind of defeating the purpose of those two functions. And in this case, your car stops. With a different configuration, your car might go, your outputs might both go to a 1. All right, so this is an SR gate or an SR latch. And we won't do it, but you can also build this with NAND gates. And you get a slightly different behavior.
So if you make it for, if the both outputs are on and it's forbidden, what would actually happen
Sorry, say that again?
if the outputs were forbidden, you know, they say it's both R and S or both 1,
Mm-hmm.
then what would actually happen to the circuit? Like, and you just say that like it's kind of impossible, but like what if you put like LED that will it keep on flashing or will it keep on?
So the way this is wired, if R and S are both 1, both outputs just go to a 0.
Straight 0?
Yeah. So it's nothing really weird. It's just slightly strange that this is not the opposite of that, because usually it is. But when you return S and R to 0, right, if I return R to 0 first, then it's like I only have S on. That's going to set the device, and it's going to output a 1. If I set S to 0 first, and then I drop R a little while later, it's like I had the R line raised, and that's going to set the output to a 0. If you do them both at exactly the same time, you can actually get unstable behaviors, though. You can actually get like a 1 that chases itself and becomes a 0, and it'll oscillate. So, but that's hard to do in practice. It's easy to do on paper, though. All right, so this is a building block for other kinds of memory. So, main thing to know about SR gates or latches, right? They have 2 inputs. One will set the device, one will reset the device. Setting means the output Q becomes a 1. Resetting means the output becomes a 0. And then Q bar is usually just the opposite of Q, unless you're doing something forbidden, like making both set and reset 1. If you build this with NAND gates, you get almost exactly the same behavior, except these inputs have to be low to do the set or the reset. So if both of these inputs are high, the output is stable, and then when you drop the set line, the output goes to 1. If you drop the reset line, the output goes to 0. So they're what would be called active low inputs, meaning that if you want to set the device, you take the set input and you pull it low instead of raising it high. But that's just going to complicate things. So we'll stick with NOR gates in this style of latch. All right, so other questions on this?
I'm still kind of confused, like, to the flow of like how the gate latch.
Mm-hmm.
So like, don't we need like 2 like values to go in here?
Yes, you do.
But the thing is like, so I assume the value here is going to be the inverse of Q.
It's going to be whatever is coming out of this NOR gate.
Yeah, but don't, to like actually for this OR gate to, let's say this NOR gate to actually output something, doesn't there need to be another?
I think there are you talking about the very beginning, like the
Yeah, the very beginning.
Yeah. So in the very beginning, it's unknown, right? But
Yeah.
there's going to be some voltage level, and it's going to output something,
Sure.
right? And if it starts off outputting a 0 and a 0, that 0, 0 is going to force us to output a 1, and then the 1, 0 is going to change that, right? So it will stabilize to something to begin with.
Oh, okay.
But we can't really predict what it's going to be. And it's possible, if everything lines up exactly right, that when you first power it on, it could be unstable. But chances are it's going to just start off as either a 0 or a 1. And turn the power supply off, turn it back on, it might come up as something opposite. Right? So it's unpredictable. But once it's got a particular value, it'll hold that value. And in practice, right, as we start building machines using these things, we don't want to rely on luck. So we would do something like, after we first power up, we would pull all the reset lines high for a moment if we wanted to force this output to be a 0. And then we don't care what it's doing when we started, because once this is high, it doesn't matter what else is going on. If that's high, this is guaranteed to be a 0. Right? NOR gates have no choice about that. And if this is low and this is low, that's got to be a 1. Yeah?
Is this kind of how like a reset switch kind of works?
It's exactly what a reset switch does, yeah. And you either have a big red button that says, reset, or you wire something into the power supply so that when the power comes from 0 to slowly hit 5 volts, it forces a signal into, say, the reset line. So yeah, that's exactly what a reset does. Yeah.
I feel like if we're going to put this in the actual circuit, where would you put the resistor and the LED?
If you wanted to see what Q was, you could run this through a resistor and LED and send it to ground. But usually this is going into something else, which is going into something else, which is going to something else, and somewhere way over here in the parking lot you've got your actual output, and that can go through a resistor and an LED. But we're going to, in a couple of weeks, probably next week actually, we're going to start building some really big circuits using these things inside. And that's where it gets really fun. Yeah?
I was just saying, can I put VCC on the other end and just the LED instead of...
If you do what?
Put VCC instead of having it go into ground.
On the other side of an LED?
No, never mind. I was thinking, it would just light up if you have a 0, right?
Yeah. Put the LED backwards, put VCC on the other end, yeah, then it lights up for 0. That's something you're going to want to remember on, I think, 2 labs from now. You're going to be building something, and you're going to need a bunch of inverters, and you can fake an inverter like that. Right? If you want an LED to light up when the output is 0, you can either run it through an inverter, and then put it through an LED as usual, or you can just wire the LED backwards. And then when your output's 0, VCC flows through it, and the LED lights up. All right, so think of this as a block, right? We can analyze why it works by going back to this and doing all of this stuff, and you want to make sure that you do this at some point on your own and it makes sense. But after that, we want to forget all that and just think of this from a system diagram point of view. It's got 2 inputs, it's got an output. If set it goes high, the output gets a 1. If reset goes high, the output goes down to 0. And when you put both of these back down to 0, the output remembers what it was beforehand. So bump the set line up, output's high. Bump the reset line up, the output's low. Okay, so it can remember the last event that occurred, but that's not the most useful kind of gate that we might want. A more typical situation would be something like this. So I'm going to call this a D latch, or a D gate. And it's going to have an output Q, and I'm not going to put Q bar up here, but there's almost always a Q bar when you have a Q. Most of these devices you buy, they just have Q bar outputs. So this has an input called D. This is our data input. And it has another input called load. And this is more like a gate. So what's a gate? It's a thing that sits in the grass, right? And you got cows over there. And when you open the gate, the cows can come through. And when you close the gate, no more cows can move from one side to the other. So if that field is empty and the gate's closed, it's always going to be empty. If you open the gate and a cow walks in and then you close the gate, there's always going to be a cow in that field. If you open the gate and you leave it open, the field may be open, may be empty, it may not be. Cows can wander in and out.
Unless they could break out.
Yeah, they can't break out. It's an impenetrable to cows fencing technology. All right, so that's exactly what happens with D-latches. Okay, this load line, this is the gate. And if this is a 0, you can have 1s here, you can have 0s here, nothing gets inside here. right? If there happens to be a 1 in here, your Q output is a 1. If there's a 0 in here, your Q output is a 0. And what happens over here makes no difference, right? Because this load line, this is the gate. There's a wall right here. You can change the input to 1 and 0. Doesn't affect what's inside. But as soon as that load line becomes a 1, whatever comes on D gets loaded in here and goes through to Q. So if the load line is high, you're loading an input bit into this thing's memory, and you're seeing that on Q. Drop the load line, and that thing is basically latched. So now if you want to remember a bit value, you could say, okay, tell me when you want to remember this, and I'll set the load line to 1, and the bit values are coming in, and you say, okay, I want you to remember the value now. So at that point, pull the load line to 0. Whatever the D value was, it's trapped in here forever. And we can see what that value is by looking at Q. So let's say Q is starting off at 0. And let's say our load line is 0. And let's say D is 0. All right, D might go high, it might go low, it might wiggle back and forth, it might be high. As long as the load line is low, Q is totally stable. Now at some point, our load line goes high. And let's say our D input is changing while our load line is high. Well, our Q is going to do exactly the same thing. And let's say at this point, we drop the load line to 0. Whatever the current value of Q is, that's the value of Q forever after. And if D happens to change after that, doesn't make any difference. So this part, where the load line is high, D is loaded into the device's memory, into the memory. Over here, D is stable. Back here, D is stable. And this is the D value that gets loaded in. So this is a bit more of a useful device for us, because we can have data coming in, and anytime we want to remember it, we just raise the load line to 1 briefly, drop it back down to 0, we've got that value stored. And this is going to eventually be how we deal with these glitches, these race conditions, because we may want the output of D to change from a 0 to a 1, but maybe it glitches through some other values for a little while. You know, maybe something happens somewhere in the system that should cause D to go from a 0 to a 1, but it's not a nice clean transition. It goes high, it goes low, goes high, it changes its mind a few times. Eventually it stabilizes to a 1. Well, if we don't load that into our latch until this point here when D is stable, we're guaranteed to load the right value. And if this output Q is what's feeding some other piece of circuitry, Q went from, no, that's going to be a lie. Forget that. When we get to a flip-flop, we'll get to the point where Q won't show these glitches on the input. But right now, while D is glitching out, Q is also glitching out. Okay, we're going to get rid of that next week. But once D is stabilized, we drop the load line. Now Q has a reliable copy of the value, even if D starts to glitch out afterwards. Okay, so we got 5 minutes. Let's build a D latch. And it's really easy to do. because we're just going to use an SR latch. So there's our SR latch. Well, we're going to use one of those. And our final output is going to come from Q. But we want a D input, and we want a load. All right, let's see if I can do this off the top of my head. All right, if I did this right, this is a D latch. So how does this work? If our load line is a 0, we've got 0 going into both of these AND gates. 0 ANDed with anything is 0, so both of these AND gates are outputting a 0, which means the reset and set lines are both 0, which means Q is completely stable. So if the load line is 0, Q doesn't change. It's ignoring the D input. So that's good. Suppose the load line is 1 and D is a 1. So D is a 1, comes down here. This input to the AND gate's a 1 from D. Load is a 1, so this input's a 1 from D. 1 ANDed with 1 is a 1. The set line goes high. But since D gets inverted, this AND gate has a 0 and a 1. The output is 0, reset is low. So if D is 1 and load is 1, the set input is turned on, and this thing's going to load a 1. And if load is high and D is low, right, D is a 0, so 0 ANDed with 1, set's going to be low. But D inverted is going to be 1 ANDed with 1, reset's going to be high. So if D is low and we say load, this is going to reset, and we load a 0 into it. If D is high and we say load, this is going to set. And when load goes low again, it's going to ignore D, and whatever value was in here, whether we set it or reset it, that's going to be latched. And so we can read the output here of the last value of D that we loaded. So that's a D latch, where this thing is an SR latch. And we're going to keep doing this. We're going to use D latches to build what's called a D flip-flop. And from a D flip-flop we can build a T flip-flop, and from that we can build a JK flip-flop, and then from that we can build computers. Right, so that's what we're going to be doing next week, is playing with these, extending them. So we'll go over the exam Tuesday. I'll make comments on it. I should get that graded somewhere in the next few days, definitely by next week. And we'll go over the exam, we'll go over the next lab, and then we'll start expanding on these devices.